Hello and welcome to another session in physics. In this session we'll be looking at the topic gravitational field. But before that, let's review the previous lesson. Welcome back. Now let's look at an introduction to gravitational field. When we talk about gravitational field, what exactly are we referring to? Well, remember that we said in our previous lessons and in our previous classes that gravitational field is classified under force fields. And we said a force field is a region or space under the influence of some physical agency or some physical activity. And some of these physical agencies are things like gravity. We have gravity, we have electricity, and then we have magnetism, and of course we have electromagnetism. So we have electromagnetic field as well. So all of these are the physical agencies we have today. And now we're starting with the gravitational field. Since a field is a region or space under the influence of some physical agency, it goes then without saying that gravitational field is a region or space around a mass in which the gravitational force of the mass can be felt. Put simply, gravitational field is a region or space under the influence of gravity. Now, you see, gravitation is the force of attraction exerted by a body on all other bodies in the universe. Gravitational force exists between a body and all other bodies around it. Gravitational force acts between all masses, and it is the force that holds planets together. It is the force that holds stars together. It is the force that holds galaxies together. So you see that each mass of body has gravitational field around it. If the universe is one big ball, there are elements inside this ball that make up this ball. Elements such as planets, of which our Earth is one of those planets. We have stars, we have the sun, we have the moon, all classified under stars, and we have our galaxies. Galaxies are like a community where you find a few planets and then you have some stars inside a particular galaxy. Some galaxies hold as much as billions of stars in them, all of them moving at very high velocity. Yet, because of the force of gravity, they do not collide with each other, because gravitational force helps to keep all of them balanced and in steady position. Sir Isaac Newton, postulated several theories because of his fascination with motion. And one of the theories he postulated helps us to understand gravitational force better. And this postulation is known as Newton's law of universal gravitation. Newton's law of universal gravitation states that every particle in the universe attracts every other particle with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. So put simply, Newton was saying that gravitational force of attraction is directly proportional to the product of the masses of the two bodies that are being attracted to each other and inversely proportional to the square of the distance between them. Now this is the sign of proportionality, which we're going to replace with equal to a constant known as G, gravitational constant, m1 m2 all over r squared. That is the equation you see right here on your slide. So the magnitude of the gravitational force of attraction between 2 point masses F is given by this equation, where m1 and m2 are the masses of the two particles, r is the distance between them, and g is the gravitational constant. that has a numerical value of 6.67 times 10 raised to power minus 11 Newton meter squared per kilogram squared. Now let's talk about gravitational field intensity. Gravitational field intensity at any point is the force per unit mass of an object placed at that point, and it is given by the expression G equal to F over m. Of course, F stands for the gravitational force and m stands for the mass of the body. It gives us this small letter G, which is acceleration due to gravity, and its unit is Newton per kilogram. Newton per kilogram, because the SI unit of force is Newton and that of mass is kilogram. It is a vector quantity and it is regarded as acceleration due to gravity. Now, what is the relationship between this G and this G? Remember, the small letter G means acceleration due to gravity, and the capital letter G is what we call the gravitational constant. Gravitational constant. So what's the relationship between two of them? The relationship between two of them, or the equation that binds two of them together, is this: G equal to Gm1 over r squared. This is the equation that binds two of them together. It tries to show us that the force of attraction between two particles of matter separated by a distance r is given by this expression here. At any point in time, you can use this, or this, depending on the parameters of the problem you're asked to solve. Note that m1 is the mass of the body that is exerting the force on the other m2. So m1 is the F, for instance, exerting a force on, say, a human that jumps up and he is made to come down, or a ball that was thrown up and later fell down. Yes, so that is m2. Now at this point, let's talk about gravitational potential. Gravitational potential at a point simply refers to the work that is done in taking a unit mass from infinity to that point. The SI unit of gravitational potential is joule per kilogram, which means it is given by energy over the mass. So the gravitational potential is given by this: V equal to minus the gravitational constant times the mass of the body divided by the distance between the two bodies, where m is the mass producing the gravitational field, r is the distance of the point to the mass, and the gravitational potential decreases as the distance increases. So we say the gravitational potential is inversely proportional to the distance, and infinitely it becomes zero when r becomes so large. The negative sign in front of this equation here indicates that the potential at infinity, or zero, is higher than the potential that is closer to the mass. Now, what about escape velocity? You may have heard it before, you may not have heard it before, but escape velocity simply refers to the minimum velocity required for an object, say for instance a satellite or a rocket, to just escape or leave the gravitational influence or gravitational field of an astronomical body permanently. Put simply, it is the minimum velocity required for an object to alleviate or exonerate itself from the gravitational influence. At that point, it is no longer under the influence of gravity. That is all we mean by escape velocity: minimum velocity required for a body to escape the gravitational influence of an astronomical body, for instance that of the Earth. Alright, so if m is the mass of the Earth, that is the bigger m, say m1 if it is the mass of the Earth, and m2 is the mass of the satellite, the small m, then the gravitational force of the Earth on the satellite becomes F equal to gravitational constant times mass of the Earth times mass of the satellite, and r squared, the distance between the Earth and the satellite. And the work that is done in carrying a mass m from a point at a distance r from the center of the earth to a distance that is so great is given as W equal to Gm, mass of the earth, and m, mass of the body over the distance from infinity to that point. Also, the kinetic energy of the body of mass having arrived at this point with a certain velocity Ve is given by half mv squared, which is also equal to this equation as well. Alright, so this is the formula for escape velocity. Escape velocity is given by the square root of 2gm over r. Of course, at this point, we know what g and m is. Also, if the mass was launched from the earth or from the surface of the earth, where the radius is r and m1 is the mass of the body, then acceleration due to gravity can be given by this equation. So what it simply means is that escape velocity can also be given by 2gr depending on the parameters of the question. Also, if a body is moving in an orbit round the earth, it has both potential and kinetic energy. The centripetal force can be calculated using mv squared over r squared or gm over r squared as well. We can also use this to calculate kinetic energy of a body in a gravitational field or its potential energy in an orbit. And the total energy will have to be the potential energy plus the kinetic energy, which will give us the total energy in the system. So we can draw the following conclusions from the equations we had, or the following postulations. The first one is that the magnitude of the total energy is equal to that of the kinetic energy of the satellite. The second one is that the kinetic energy of a satellite or a body orbiting in space increases as the radius of the orbit decreases or reduces. The third one is that the kinetic energy of a satellite in an orbit increases as the speed of the satellite increases. So we can say that the kinetic energy of a satellite is directly proportional to the speed of the satellite itself. And finally, the final postulation is that the potential energy of the satellite in orbit is twice its kinetic energy and is of opposite sign. For more information, please do well to go through the note attached at the end of this lesson. Thank you very much for joining us in this lesson, and to refresh your memory on what we've just discussed, please take the tests that will appear on your screen.